All right, this is 4.3, part 2. So I want to do a little bit more with finding the intervals of concavity and then maybe a little bit with being able to sketch a curve from given information. All right, here's the first example. So we have this function. We're going to pretty much find everything. So the first thing to do would be to go ahead and find the derivative. So we're going to say f prime of x equals 4x cubed minus 12x squared. Then we're going to go ahead and factor it. So it's easy to find those critical numbers. So let's see what we can take out. Looks like we can take out a 4 and an x squared. That would leave us with x minus 3. And we should be able to tell what the critical numbers are there. So we have critical numbers. Let's say the critical numbers are whatever makes this equal 0. So we're actually setting this equal to 0. And we would say the critical numbers are 0 and 3, right? So what we do is we make a nice sign chart with that. With those, that kind of sets up the intervals. So we have 0 here, and we have 3 here. And then we'll put our factors off to the left. So let's go ahead and put those factors there. So we got x squared, 4x squared, and x minus 3, and then the result to determine when is the first derivative positive, when is the first derivative negative, etc. So let's try to plug in some test points. So maybe -1, just to the left of 0. That would cause this to still be positive. And then -1 minus 3, that would be negative. And so the overall result would be negative. And then between 0 and 3, maybe an easy test point would be 1. So we plug that in, that would be positive. 1 minus 3, that would be negative. That would be overall negative, so it doesn't look like we have a sign change there. And then we have a test point of 4, so that would be positive, positive. The result would be positive. All right, so that gives us some information. We actually know, based upon this, if you look here, we go negative to negative, no sign change. But at 3, right at 3 here, we go from negative to positive. Now again, whenever the first derivative goes from negative to positive, that means, according to the first derivative test, that your graph would look something like this, and your first derivative would go from negative to positive, and you'd have a low point there. So there's a minimum. So again, because it changes from negative to positive. So we have a minimum, a local minimum. And local minimum, we can just plug the 3 into the original function to figure out what we get. So we plug it into that function, and I got -27. So that's a local minimum. That's important. We have no local max because we have no sign change from positive to negative. So we have no local maximum here. All right? So that's really, and then as far as the intervals of increasing and decreasing, you can tell whenever it's negative, the first derivative is negative, that means the function is always decreasing from negative infinity all the way to 0 because of what we see here. And then it levels out here. And then it's still decreasing the whole time from 0 to 3. And then finally the function starts going up again from 3 on, okay? Because the first derivative is positive. Now, same problem, we're going to go ahead and continue on, and we're going to find the second derivative. So we're using this first derivative, and let's go ahead and find the second derivative so we can determine concavity. So second derivative, take that same function. We would say the second derivative would be 12x squared minus 24x. We do the same thing. We would set it equal to 0 and try to find those. I don't know if we would call them critical numbers, but it's the same sort of deal. So we set it equal to 0. We factor it. So we take out a 12 and an x. That leaves us with x minus 2. So we can tell those key numbers. I'll go ahead and call them critical numbers. So we got 0, 0, and 2. That sets up your sign chart, your intervals. So we have 0 here, we have 2 here, Probably don't need my sign chart to be that big. That's all right. And I put my factors here so I can determine the intervals of concavity. All right, so I'm going to try some test points. So maybe to the left of 0, again, like maybe -1. It's a test point. That would be -1. That would be -1. That would be a result that's positive. I'll try 1, so that would be positive, negative, and then negative. Try a test point like 3, so that would be positive, positive. The result would be positive. So clearly the result here tells you whether it's concave up or concave down on those particular intervals. So we would say concave up on, and we'll come up with the interval for that, concave down on. And all right, so concave up, it's wherever the second derivative is positive. So we can see that interval. That would be from negative infinity to 0. So we'd say negative infinity to 0, union with wherever else it's positive. So 2 to infinity, and that's concave up. Concave down is wherever, the second derivative would be negative. So we'd say concave down on the interval from 0 to 2. And then the inflection points are going to be wherever the second derivative changes sign. So inflection points are, and so we would look for sign changes. So we see a sign change here, right here. So that means at 0, there's actually an inflection point. It goes from positive to negative, concave up to concave down. So the inflection points are 0, something. Got to figure that out. And then also from negative to positive, we went from concave down to concave up. So we have an inflection point at 2, something. Got to figure that out. So all we would do is plug that into the original equation. So I did that work. I plugged in 0 into the original. So I got 0, 0, and 2, -16. Okay? And then as far as the curve goes, let's just kind of, get a sketch of the curve to see if really all these points line up, all these key characteristics. So let's say I went ahead and I just graphed it on the calculator just to get an idea. So, or just use the information that we found out. So we found out that the minimum was 3, -27. So I'm way down here at 3, -27, let's say. That's a local minimum. And it kind of goes like this. And then it goes up. And let's look at some of the things we figured out. So we said that the function was decreasing really the whole time from negative infinity all the way to 3, although at 0 it leveled out because the first derivative was equal to 0. Well, we see that. It goes down here, but then it levels out. Actually, if I had graphed it better, kind of levels out there, and then it does still decrease. And then what else? And then it says, that we got our minimum there, yeah, and then it starts increasing from 3 on. So good there. We didn't have any local max. Then concavity. Well, it says it's concave up from negative infinity to 0. So we're saying all this is concave up, but then it levels out. And then, let's see, concave up again. By the time it gets to like 2, they're considering this concave up to infinity. And they're saying that it's concave down from 0 to 2. Analytically, we figured out that it's concave down here, which makes sense. You can see that. And then this, again, the blue would be more concave up. And inflection points, 2, -16. Well, at 2, -16, this is where it changes concavity because it went from concave down to concave up there. This is 2, -16. And then at 0, 0, there was a change in concavity because it was concave up. We're considering all this concave up. It leveled out, and then it switched, and it went concave down for that little bit from 0 to 2. And I think that's all the parts of that particular problem. Let's try to do this challenging problem. These are like puzzles, trying to figure out all the pieces. So let's just do a piece at a time. sketch a graph that has all these given conditions. Well, I won't necessarily take the time to let you write all these down. Of course, you can pause it for that, but I'm going to go right to it. What you do is you would start off with, all the things that you know for sure, like the points probably. So 2, -1. So let's put dots there. 2, -1, 0, 0. So clearly we've got those dots. And then you just kind of go from there. So, like f prime of 2 equals 0. At least we know right here at 2, it somehow levels out. So it's going to level out there because the slope of the tangent line is equal to 0. That's what the first derivative is right there at 2. Now, it says right here that the first derivative is less than 0 if x is between 0 and 2. That means the function is decreasing. If the first derivative is less than 0, then that means the function is decreasing. So that means from 0 to 2, the function would have to go down to get to that spot. And then let's see what else. The function is increasing because the first derivative is greater than 0. Again, first derivative means how is the function changing? It's the rate of change of the function. So x is greater than 2, it must be increasing. So at least we know it's going up at this point. And then let's see what else we can gather. Looks like the second derivative is describing the concavity. So we got concave down, looks like it's less than 0. Concave down from 0 to 1. So actually my sketch would look a little bit more like this from 0 to 1, actually more concave down. And then, and when x is greater than 4, so that's interesting. So somehow when you get over 4, it kind of becomes a little more concave down, okay? From what we gather here, x is greater than 4, concave down as well. Second derivative is greater than 0. Again, this is concave up. If x is between 1 and 4. So it's saying that all the time that it's between 1 and 4, it's concave up. So that would be concave up from 1 to 4. So all that area there kind of looks concave up. And again, at 4 is where it switches the concave down. And do we have anything left? Oh, and then this last piece. Oh, no, this one. This is a big one. It says the limit as x approaches infinity is actually equal to 1. So a little oops there because it looks like I kind of surpassed that a little bit. So it looks like we should have a graph that approaches 1. So that means that's a horizontal asymptote. So it would actually become concave down again, and it would approach 1 because as the limit as x approaches infinity, the limit's 1. All right. Remember, that's always horizontal asymptote. Now, the last step, it says f of negative x equals f of x, which is a fancy way of saying that it's symmetric with respect to the y-axis. It's an even function, so it makes no difference whether you plug in a positive x value or a negative x value. It gives you the same y-coordinate. So we basically just reflect it over the line, over the y-axis, I should say. Okay. So if we reflect it, it just looks identical, and so it would look, something like this, roughly, kind of like that, just perfectly symmetric over the line. And the other thing is we have inflection points. So we have inflection points wherever we change concavity. And you'll notice they kind of told us that because we have a change in concavity right here at 1, because it was concave down here from 0 to 1, and then from 1 to 4, it was concave up. So that means at 1, we've got an inflection point. So we've got inflection point, inflection point at, I'll just give you the x-coordinate, at x equals 1, and is there another change in concavity? How about right here at 4, where it was concave up, where the green is, and then it changed to concave down. So x equals 4. We don't have enough information to actually get the y-coordinate. We just can sketch a rough sketch of where the inflection point occurs, at least the x-coordinate. All right, that should do it. Between the two videos, you should have a good amount of information. The only other thing is like reading graphs. You should be able to look at this graph and be able to tell like which one is the original graph, kind of like what we were doing before. You know, which one is the derivative, etc. You know, there's one of these that starts off as cubic, you know, something to the third power, and then it goes quadratic. And actually, what is this one? This one is actually, we'll do a little bit of this one in class. All right, should be good enough.